Hello, physics students. In this lesson, I want to take you through the calculations for circuits, whether they be series or parallel. We're going to come back to using Ohm's law and be able to calculate current, resistance, and voltage in all the parts of the circuit. So please have your notes ready and we'll run through a few of these examples together. One of the key pieces to understanding how circuits work with the math and Ohm's law is to really understand how resistance works in a series and in a parallel circuit. So as we look at the circuit on the left, you'll see there's one path for the current to take through resistor 1 and resistor 2 and back to the voltage source. This means this is a series path, whereas in the current or the circuit on the right actually has multiple paths. It could branch and go down to resistor 1 or branch and go down to resistor 2. Therefore, it's a parallel circuit. When we talk about resistance in a series circuit, like the one on the left, we add the two resistances together to get what we call the equivalent resistance. So in this case, we just take R1 plus R2. So if R1 was, say, for example, 5 ohms and R2 was 6 ohms, we get a total resistance of 11 ohms. All right, so that's kind of how that works with just a series circuit. Parallel, on the other hand, we're going to have to do a little bit more math because as you add more branches in a parallel circuit, it actually draws more current from the voltage source. So the equivalent is a 1 over relationship, or 1 over the equivalent resistance is equal to 1 over the first resistance plus 1 over the second resistor, and so on and so forth. So in the end, once we add these inverses together, we'll take the reciprocal to find out what our equivalent resistance is. I want to go through a few examples with you in the next few slides. So I want to take you through a few examples of how to calculate overall current and resistance and voltage in each of these circuits. So let's take a look at the first very basic circuit. We have a series circuit here where the current is traveling through one 3 ohm resistor and then back to the voltage source again if the switch was closed. We're going to come back to our idea of Ohm's law where we have voltage, current, and resistance all related to each other. So if I wanted to find out how much current is actually traveling through this circuit, I need to use the voltage and the resistance. In this case, I can take the 9 volts, plugging those in for voltage over the 3 ohms, so that gives me a current of 3 amps. Even when we have more complex circuits, we're always going to try to simplify into one of these basic types, either series or parallel, and do the math just like I did in this example. So let's take a look at what happens if you calculate in a series circuit that now has more than one resistor. So before we do the math, if I just take 9 divided by 3 and get 3 ohms, I'm not going to end up with the right amount of current because I have to factor in the fact that that's going to actually go between two resistors. So I need an equivalent resistance. For series, I simply add the resistors together. So my equivalent resistance becomes 3 ohms plus 3 ohms, or 6 ohms. Now I can substitute that in and I end up with 1.5 amps of current when there are two resistors. All right, notice this would be the same as if I was to replace both of these 3 ohm resistors with one 6 ohm resistor. I would get the same exact answer. That's why we call this an equivalent resistance. All right, well, what does that mean when we talk about parallel? Well, parallel is different because it provides an extra branch for that current to travel through the circuit. So therefore, the rules for parallel have to come into play, where to find that equivalent resistance, I cannot, repeat, not simply add 3 ohms plus 3 ohms. I have to add their inverses. So the inverse of 3 plus the inverse of 3, and then take the reciprocal of that final answer, gives me 1.5 ohms. So these two work together, these two 3 ohm resistors are pretending or behaving like they were a 1.5 ohm resistor. Well, that should already tell you in your gut that less resistance in this equation equals more current. And that's the exact case is true because 9 volts divided by 1.5 gives me 6 amps. So in this parallel circuit with the same type of resistors, I'm now drawing more current. So keep that in mind. As you add more branches, you're actually able to draw more current through your parallel circuit. Okay, well, what does that mean? When we go through these, we have to think about basically 3 to 4 main steps, okay? So if I want to calculate what happens in this, I always have to come back to finding that equivalent resistance first. So whatever these are, so if this first resistor is 2 ohms and this one is 4 ohms, to find out all these values, I've got to come back to those rules, all right? So the first rule I'm going to come back to is calculating my equivalent resistance. That is what the battery experiences, okay? So the resistance of the battery. So sometimes we say R sub B. It's how much resistance the battery is going to experience in that circuit. For series, I can simply add the resistors together, so I'm going to get a total resistance of 6 ohms. So I'll put that down here in the chart for the battery, 6 ohms of resistance. My next step is going to be finding out what the current is. I know if this is a 12-volt battery, they might tell me that in the problem, that divided by 6 ohms of equivalent resistance gives me 2 amps. So that means there's 2 amps of current flowing through this circuit. Then I have to remember my rules. And for series, the current stays the same across all resistors. So if there's 2 amps of current going across the first resistor, like you see here, that means there's going to have to be 2 amps of current in the other resistor that's connected in series. Series has the same current for each resistor. But the voltage in a series circuit is added up. So when I take a look at finding that voltage, that's my last step. I know that the series is the same, so then I can come back to Ohm's law, plugging in I times R, current of 2 amps times the resistance of 2 ohms, gives me 4 volts. 2 times 2 is 4. To find current or voltage, in the other resistor, I'm going to do the same thing. Current, still 2 amps, remember that's the same in series, times resistance of 4 ohms gives me 2 times 4, or 8 volts. 8 plus 4 should add to your total voltage here as a check. Remember, the voltage is added across those. All right, so those are putting all these ideas together. This is the process that you would take when you're solving these problems. All right, what does this look like for a parallel circuit? The same exact thing, except in parallel, we're going to pay really close attention to the parallel rules. For parallel, current is added across each resistor, and voltage is the same across each resistor. All right, so always think about the first step. We're going to come back and calculate our equivalent resistance. Parallel, mind you, we're going to use the inverse. So the inverse of resistor 1 plus the inverse of resistance 2 will then take the reciprocal of that answer, will give me 2.4 ohms. That becomes the resistance that the battery experiences. If it's a 9-volt battery, the problem might tell you that, because it is in, we want to find out what the current is that the battery is that's leaving the battery, we'll use Ohm's law to calculate that out, right? So it's going to be the 9 volts divided by the resistance will tell me what that current is. All right, in this case, it's 3.75 amps. But be careful, that 3.75 amps is not happening across each of the branches because in parallel, the current adds. So whatever I need to do is I need to find out how much current is happening in each of the resistor branches. To do that, I use what I know about the parallel, and I will know that the parallel branch, the voltage stays the same. So when I'm calculating the branch current, I can use the voltage of 9 volts because that will not change. And 9 volts here, and 9 volts across this branch, and 9 volts across this branch. The resistances are often given for those branches. Now I can use Ohm's law and calculate the current across 1 and 2. All right, so I can easily find the voltage, which is 9 volts divided by my resistance of 6. So I'm going to get 1.5 amps for the first one. Same thing, 9 volts divided by 4 gives me 2.25 for the second. Those added together, 2.25 plus 1.5, should equal the 3.75 amps that's coming from the battery. Those checks are always useful when you're working with these circuits. All right, a last example. As I'm going through, I have a few different numbers here. I have a 6 ohm, 4 ohm, and a 3 ohm. There's 3 branches. Again, in parallel, the voltage is the same in each branch. So it's 9 volts across all of them. I was able to find out what the current is that's coming from the battery because I could find the equivalent resistance of all these resistors. To do that, I first needed to use my inverse addition rule. So once I do that, I find the reciprocal, and then I know that that's 1.5 ohms. Now I can find out how much current is coming out of the battery by using the voltage for the whole system and divided that by the resistance, the equivalent resistance. That then gives me the current. Knowing that this is parallel, we talked about this already, but that means that the voltage is the same in each path. Then I can calculate I1, I2, and I3 using our Ohm's law, right? So once I do that, I know the current in each branch. If this is number 1, it's going to be the voltage across number 1 divided by the resistance across number 1. Okay, in this case, it's 9 volts divided by 6 ohms, and that gives me my 1.5 amps. I just repeat that process for each of the other resistors. These added together should equal my resistance or my current across the battery. All right, to summarize, and this is something that you should definitely add in your notes, is that difference between the series and the parallel circuits. When we talk about voltage, the voltage adds in a series circuit, and it's the same across all the branches, the same as the battery across all the branches in a parallel. Current is the same across all of the resistances or resistors in a series circuit, and it adds across all the branches to make your total current in parallel. The key to all this is understanding how to find resistance. Resistors added together for that equivalent resistance in series is a simple addition. For parallel, you need to add the 1 over and then take the reciprocal to find your equivalent resistance. So please have this in your notes. This is a really helpful, useful guide. All right, the last example I wanted to go through is what happens if you have a combination. This circuit actually is both series in this branch, but then this branch is parallel with this branch. So it's a series inside a parallel circuit. Well, once again, we're going to try to simplify this by first combining the resistors that we have on the branch. These are in series, so we can use the series rules to combine those. So I can simply add those together. Then I know that this has now an equivalent resistance of 6 ohms. I can then use a parallel, I can redraw this to be simply a parallel circuit. And in doing so, now I can use my equivalent resistance for parallel to find out how many ohms that equivalence is. And of course, if I want to find current in this, I would then come back to Ohm's law. Current is equal to the voltage of the battery divided by the resistance. In this case, the resistance of the battery or the equivalent resistance. So I'd have 9 volts divided by my 3 ohms. So I have a current of 3 amps. Okay, so hopefully this makes sense. When you're doing combination circuits, simplify it. I like to draw the next progression and then use the rules as series or parallel as they apply. Please reach out if you have any questions. Thanks, and have a great day.